So the last topic we're going to talk about for trusses today is we're going to talk about zero force members. All right. So so oftentimes you'll be given a truss, and depending on how the truss is being loaded, there may be some cases when the truss is some members of the truss are supporting no load. All right. So these members of the truss that support no load are called zero force members. Right. So what you can do to make your analysis a lot simpler is you can often identify zero force members by inspection. Inspection, uh, or you can draw the free body diagram at the joint. In the joints, and then it becomes very obvious that the only way that equilibrium would be satisfied is if all the forces within the joint would have to be equal to zero, or a certain force within the joint would have to be equal to zero. So this concept is best explained by an example. So we're going to look at our truss we have in this situation. All right, and we're going to draw free body diagrams at a couple joints. So the first one that we'll do is we'll draw the free body diagram of joint A. All right, so joint A on this truss on the left-hand side of the screen, that is here. All right, so joint A has two members that connect to it, one that goes from point A to point F, and one that goes from point A to point B. All right, so we can so if we drew our free body diagram, there would be a force that would go from point A to point F, and there would be a force that would go from point B A to point B here. All right. So in order for the sum of all our forces in the x direction to be equal to 0, and the sum of all our forces in the y direction to be equal to 0, since FAF and FAB are perpendicular to one another, the only way this can be true is that if FAB would be equal to 0 and that if FAF would be equal to 0. All right? So therefore we can say that these two members, FAF and FAB, would not support any load of the load caused by the external force P. Right? So we can do the same process, but with the joint at D. So if we draw the free body diagram at D, all right, what we'd end up getting is there'd be a force that goes from point D along member DC, so we'll call that FDC. Then there'll be another force that will go from point D to point E, which we'll call FDE. All right, now these two forces are separated by an angle theta. We can draw our XY coordinate system like this, where Y would be parallel with FDC. So if we took the sum of all the forces in the X direction and set that equal to 0, we would get that would be equal to negative FDE times the sine of theta. All right, and then if we looked at f of y and set that equal to 0, you would get minus FDC minus FDE cosine theta. All right. So if we look at our sum of the forces in the x direction, the sine of theta is only equal to 0 when theta is equal to 0. Therefore, but we know that theta is not equal to 0. So since theta does not equal 0, we know that the only way this equality can be true is FDE must be equal to 0. All right, and then if we plug FD equals into 0 into this equation here, we'll end up getting that negative FDC would be equal to 0. Therefore, we can say that FDC is equal to 0 as well. All right, so we can say that these two members will not hold any force either. So we end up getting here is that we can treat this truss system as being a simplified version of itself, where it would just have a few members. We'd have here, all right, where this is joint. We have a pin at joint F. We have a pin at E. We have a pin at C, and we have a roller at B that support this truss. All right, and we have the external force P that's being applied to that truss. But that's all we have. So we'd only have, and we have another joint here. All right, so another member here. So we went down from having a 1, 2, 3, 4, 5, 6, 7, 8, 9 member truss to a 1, 2, 3, 4, 5 member truss. So we went from 9 members that we had to analyze down to 5 members. All right. So by using this technique, you can significantly reduce the number of members that you need to analyze. All right. So we can do the same process on the next example. If you want, you can stop the video now and try it on your own, and you can check with me afterwards. All right, after you're done going through the next example. So try to identify the next example on the next page on your own to identify what are the zero force members. So identify the zero force members. All right, on the next page. So that's where I'm going next. All right. So, all right. So in this example problem here, just looking at the problem, we have a few cases that look like candidates that would have no force. So I'm going to look at joints D. All right. So if we look at joint D, we can take the free body diagram at D. All right. If we look at joint D, it has 3 members going into it, so it'll have 3 forces. One would go from point D to point E. One would go from point D to point C. All right, we have another force that goes from point D to point A. All right, now we are given that the force that goes from the member from point D to point A is perpendicular to the other members. All right, so what we can do is we can set our XY axes. All right, where our x-axis would be going along FDC, and our y-axis would be going in the opposite direction as FDA. So we can use this coordinate system for our equilibrium equation. So if we do that, and we set our sum, our forces in the y direction has to be equal to 0, we would get that would be equal to minus FDA. All right, therefore FDA would have to be equal to 0. All right, so we can eliminate this structure. This we don't have to consider the member from point D to point A in this loading. All right, so we could also really quick just say that the sum of all the forces in the x direction is 0. Therefore, we get FDC minus FDE. All right, so we could say that FDC would be equal to FDE. All right. So we can do this, repeat this process, but now at point C, where we would get, if we draw the free body diagram at point C, we'd get the force within member CD, and we get the force within member CB. All right, and then we'd get our force that goes from point C to point A, which we'll call FCA. All right, again, we can make our lives a lot easier if we draw our coordinate system where the x-axis goes along FCB. So if we sum all of our forces in the y direction first, we would get FCA times the sine of theta. All right, since theta does not equal 0 in this case, the only way this equality can be true is that FCA would have to be equal to 0. All right, so since FCA is 0, we can cross it out on our truss diagram. All right, and then if we did the sum of all the forces in the x direction now, we'd just be left with FCB minus FCD. So we can say that FCB would be equal to FCD. All right. So if we look at our truss, we can redraw our truss that we have over here. We can draw a simplified version of it. So we'd end up with just a 3-member truss in this case, where we have a rocker joint at point A. We have a pin at point B. And we have a external force applied at point E. All right. So since the force within DE is equal to the force within DC, which is equal to the force within CB, we can say that we can treat those 3 members as being a single member, which we'll call FBE. All right. So we went from having a truss that had originally, originally it had 1, 2, 3, 4, 5, 6, 7 members, down to only 1, 2, 3 members. Okay? So eventually what you'll be able to see is that if you have joints that have only 3 members in them, you can just look at those 3 members, and if there's no external force that's being applied to them, or there's no support reaction like we have in these cases, typically those are candidates where you have a 0 force member, especially if 2 of the members that are going into the joint are going along the same direction. Right. So that concludes this recording.